Brownlee, Jacqueline Brownlee, hold on, there's a bit come up here, right. Jacqueline Brownlee, one of the leaders of a youth club in Lark Hall, has asked Kaz if we do visits to such groups. And I replied to her and included Gordon in the email that we do public outreach. Now, Gordon's going along to do a presentation, but the date's still to be sorted. But if anyone else would be interested in going along with Gordon with their scope, if you can let Gordon know, just to help out in that, you know, I don't know how many kids are going to be there anyway.
I've asked her what her expectation is, Alice Amanda. You know, I've given her a suggestion of what I could do. You know, I've done it before.
Aye.
So I'll wait till she gets back to me and we'll work out some sort of program.
Aye. Aye, and then you can let me know, and I can message the members that if any of them want to tag along with you with their scopes, you know, anybody that's close to Lark Hall, you know, or whatever that would be interested in going along. Right, right. Now it's over to Roy for space news.
Thank you, Alice Amanda. I said I haven't done this for a couple of months. Hopefully I can remember which bits to press.
Well, I had in brackets there, thank Roy, and then I was going to thank you.
And I was about to clap.
And then I realised, no, I'm not to thank him.
I know, and I was about to clap. I think we're all next.
Oh, here we go, from beginning. Right, hopefully, can you see the screen all right?
Yes.
Good, okay. Switched on, here we go. So lots of interesting things have been happening over the summer break, but as usual, I've tried to keep the space news section only about recent discoveries that you might not have heard about. However, I'd be rather surprised if none of you had heard about the James Webb Space Telescope, which I still think after Mars exploration is one of the most exciting things happening at present. After many delays, it's time to take out your pencil and lightly circle December the 18th on your calendar. According to NASA, this is the new launch date. I know, it means that date's always shifting, but this time the telescope's actually been put in its shipping container for its voyage to the launch site in Kourou, French Guiana. The European Space Agency has been delivering all the rocket components to the launch site, including the upper stage and the launch fairing. So keep your fingers crossed, the delays are now over and that James Webb's ready to fly off into space. And so back to my other favorite topic, Mars. Mars is bombarded with radiation. Without a protective magnetic shield and a thick atmosphere like Earth's, radiation from space has a nearly unimpeded path to the Martian surface. Our machines can roam around on the surface and face all that radiation with impunity, but not humans. For humans, all that radiation is a deadly hazard. So how can any potential human explorers cope with all that? Well, they're going to need shelter. They're either going to have to bring it along with them or build it there somehow, or maybe not. Maybe they could use natural features as part of their protection. A new study using data from MSL Curiosity has uncovered how Mars's natural landscape features can provide some shelter from radiation. Specifically, it shows how Martian buttes provide protection from high energy particles from space. The study is entitled Directionality of the Martian Surface Radiation and Derivation of the Upward Albedo Radiation, and it was published in the Geophysical Research Letters. The lead author is Guoying Gan from the University of Science and Technology of China. When MSL Curiosity landed on the surface of Mars in 2012, it carried in its payload an instrument called the Radiation Assessment Detector, or RAD. It detects and measures harmful radiation on Mars that comes from the sun and other sources. It can also assess the hazard that radiation poses to any microbial life that might still be existing on Mars. RAD's about the size of a toaster, and it sits unobtrusively on Curiosity's top surface. One of the areas the MSL studied with RAD is the Murray Buttes region. The Murray Buttes region is on Lower Mount Sharp in Gale Crater. Curiosity was there primarily to study geology, especially the sandstone features and a type of layering called cross-bedding. But while there, RAD kept gathering data, and that data showed a drop in surface radiation. MSL Curiosity spent 13 sols parked near the butte and the Moody Buttes area. It primarily conducted the surface science and drilling operations while there. But RAD was still active, giving scientists a 13-day reading of radiation data in one location. The RAD data showed that while near the butte, there was a reduction in radiation dosage of about 5%. The research team then constructed a sky visibility map, showing that 19% of the sky was obscured when the rover was next to the butte. This isn't a scientific done deal when it comes to protecting future human explorers from radiation, but it's important data. Any mission to Mars involving humans will need layers and layers of contingencies. In the event of an emergency of some sort, it will be vital to keep astronauts' radiation doses as low as possible. In fact, the entire mission will be planned to keep annual exposure within limits. It's not too difficult to imagine planetary explorers making use of whatever radiation shelter they can as they try to contend with an equipment breakdown or other mishap. Detailed radiation maps take into account sky exposure and terrain and anything else that might save lives. Now we turn to Vesta and what formed the strange troughs you can see. New research suggests that the humble asteroid Vesta may actually have cracked open just like an egg. NASA's Dawn probe was launched in September 2007 to study the two largest members of the asteroid belt, Ceres and Vesta. But it didn't have to work hard to get there. According to Christian Klimczak, Associate Professor at the Franklin College Department of Geology, while most asteroids are indeed irregularly shaped and grey, they're far apart, and NASA's Dawn spacecraft didn't have to maneuver around any asteroids to reach and explore Vesta. So it's not like films like Star Wars where you see spaceships flying in and out between all the asteroids. Vesta is particularly intriguing among the asteroids because it's large enough to have an iron core, mantle, and a crust, not unlike the Earth. That's why astronomers consider Vesta to be a planetesimal, or an almost planet. Vesta was on the way to becoming an Earth-like planet too, but planet formation stopped along the way, early in the history of the solar system. Therefore, studying Vesta helps us understand the very early days of our planetary neighbourhood and how our own planet formed. Except things didn't go as well for Vesta as it did for Earth. For one, the little asteroid was struck by two other large asteroids that managed to leave impact craters so big that they almost cover its entire southern half. By studying Vesta closely, researchers like Klimczak try to understand the evolution of the planetesimal. Rock properties are influenced by environmental conditions, like surrounding stresses and the presence of water. Since Vesta is much smaller than Earth, or even the Moon, it has a weaker gravity, and rock would deform differently near the surface than what we see from Earth. Especially interesting are the two large troughs which surround the impact basins. Planetary scientists have long assumed that the troughs were created by the impacts, but that relationship has never been firmly established. Our work used crater counting methods to explore the relative age of the basins and troughs, Cheng said. The fewer the craters a region has, the younger it is. And so by comparing the number of craters between the troughs and the basins, the researchers can explore their relative age. Consequently, counting the number of craters of various sizes in a given area allows us to determine how long they've accumulated and consequently how long ago the surface formed. Our results show that the troughs and basins have a similar number of craters of various sizes, indicating they were actually of a similar age. However, the uncertainties associated with crater count allow for the troughs to have formed well after the impacts. But how exactly did the troughs form? The leading hypothesis suggests that these troughs were fault-bounded valleys, with a distinct scarp on either side that together mark the sliding of a large block of rock. However, rock can also crack apart and form such troughs, an origin that hadn't been considered before. Our calculations also show that Vesta's gravity isn't enough to induce surrounding stresses favourable for sliding to occur at shallow depths. Instead, the physics shows that the rocks are actually more likely to crack apart. Excuse me. Therefore, formation of these troughs must involve the opening of cracks, which is inconsistent with the leading hypothesis in the scientific community. Taken all together, the overall project provides alternatives to previously proposed trough origin and geological history of Vesta. Results that are also important for understanding similar landforms and other small planetary bodies elsewhere in the solar system. But anyway, whatever happened on Vesta, it was certainly quite a nasty accident. Dust on Mars gets everywhere, including on top of ice deposited during one of Mars's previous ice ages. Just how that dust affects the ice is still up for some debate. Adding to that debate, a recent paper by researchers at Arizona State University has laid out a map between the dust content of a glacier and the brightness of its ice. As with many climate-related interactions, the seemingly simple interface between the ice and the dust is much more complicated than it appears. The team used pictures from the Phoenix Mars lander and the Mars Reconnaissance Orbiter to build a model that would predict how bright snow and ice would be here on Earth, and then flipped that approach to estimate how the dust on Mars affects the brightness of ice deposits on that planet. It turns out a lot of ice on Mars is covered in dust, and the colour of that dust makes a huge difference to the ice it covers. Darker dust strains would attach more heat, making it more likely that the ice it covered would melt. Alternatively, ice that isn't covered by dust is reflective, making it less likely to melt in the much weaker Martian sun. If any ice does melt due to the increased solar radiation it receives, the dust piled on top of it also makes the resulting water less likely to evaporate away into the Martian atmosphere. So the Martian dust itself might play an important part in any Martian hydrological cycle. So far, this is simply a theory backed up by some preliminary data collected by orbital satellites and one lander. To gain further credibility, the theory will have to withstand the further scrutiny of ice samples collected off the planet's surface in the future. Either way, if humanity ever hopes to set up a permanent base on Mars, it's going to be important to understand how all the complex factors present on the red planet interact to create its local environment. In some applications, bigger lasers mean better lasers. That's the case in astronomy, where lasers are used for everything from telescope calibration to satellite communications. The European Southern Observatory and some of its commercial partners have developed a laser 3 times more powerful than the existing industry standard. With that increased power level, the new system has the potential to dramatically improve the way telescopes deal with one of the most fundamental problems in ground-based astronomy, atmospheric turbulence. Regular atmospheric turbulence is commonplace on Earth, and it's the cause of what the human eye perceives as the stars twinkling. However, on a telescope, turbulence that is unaccounted for could lead to entire data sets being thrown out. Telescopes have a standard technique to eliminate any such effects. They calibrate using a known stable star. The obvious problem is sometimes there are no stars they can use to calibrate to. So scientists came up with a way of making an artificial star that would allow observatories to calibrate against a stable observable object, no matter which direction they were facing. That technique involves blasting sodium atoms 90 kilometers up in the atmosphere with a laser. Today, that technology exists as the 4 Laser Guide Star Facility, which operates the ESO's Very Large Telescope. Coming in at a respectable 22 watts of power, this calibration tool has been essential to the VLT's successful operation. However, the more powerful the laser brought to bear on the sodium atoms, the more stable the calibration star. So ESO has bumped the power level up to 63 watts, almost a 3-fold increase over the existing system. That increase is thanks to work on developing an advanced Raman fiber amplifier laser source created by MPP Communications, a Canadian company that serves as one of ESO's commercial partners. They weren't alone in developing technologies to help improve the calibration lasers. Toptica Photonics in Germany also specializes in frequency chirping systems that allow the laser to bounce back and forth between several different frequencies. Larger bandwidths means more excited sodium atoms and a bright star to use for calibration. Calibration isn't the only thing that improved lasers are useful for, though. Satellite communication systems have become much more important lately, with SpaceX's Starlink leading to a new era of space-based communications. However, they are limited in their use of one of the most high-speed data transfer techniques. Optical communications between satellites and Earth itself is complicated by the same atmospheric turbulence phenomena that can throw off telescopes. With this higher power laser able to create more stable calibration points for these systems, optical communication becomes a much more appealing data transfer method. Scientists plan to install the new laser system, part of the Canopy Laser Guide Star Adaptive Optics System, at an ESA observatory in Tenerife in Spain. If the system proves its value, it will serve as a basis for other improved calibration and communication tools throughout the expanding observational and networking platforms spread throughout the world. Conventional theory states that light stars like our sun gently blow off all their layers when they die, while heavy stars explode as a supernova. But for some reason, we are so far failing to find any supernova from stars heavier than 18 solar masses. Now a team led by SRON astronomers finds a new clue that fuels this apparent mystery. The research team looked at the luminous infrared galaxy ARP 299 using the X-ray telescope XMM Newton. Their aim was to measure the abundances of several different chemical elements that are normally produced and expelled into space when massive stars explode. They found a mismatch for the heavier elements of iron, neon, and magnesium compared to existing models for how stars should enrich their environment. This is another indication that very heavy stars don't go supernova, says lead author Zhangji Mao of Strathclyde University. When the researchers compared the measured amounts of iron, neon, and magnesium with existing model calculations, the results appeared quite different. If we remove the expected contribution from supernova with masses above 23 to 27 solar masses to the chemical enrichment from model calculations, the difference between our model and the observations are suddenly a lot smaller. Astronomers still don't understand why stars from around 18 solar masses would disobey the conventional theory of stellar evolution and refuse to go supernova. One possible explanation is that it might immediately collapse into a black hole without the explosion, says co-author Aurora Simonescu. We've now found more evidence that the end of life of massive stars could look very different to what we thought it would be so far. It could be more of a quiet passing away than a big cosmic fireworks show. China built the Great Wall of China, and it's now going to build something equally big by the looks of it. China now has a space station, robotic missions to the Moon and Mars, and it's working on a human mission to the Moon. They're getting ambitious. In its latest 5-year plan, China outlined a proposal to build an ultra-large spacecraft spanning kilometers, something that would be 10 times larger than the International Space Station. Though there's no special details released yet, it would be an enormous undertaking, costing hundreds of billions of dollars and taking hundreds of rocket launches. Thanks to COVID-19, the world's supply chains are all snarled up. One bizarre impact is in Florida, where hospitalizations for COVID are causing a high demand for liquid oxygen. That's the same oxygen that rockets use for propellant. The shortage has gotten so bad that SpaceX is anticipating launch delays for upcoming rockets, both in Florida and California. SpaceX President Gwynne Shotwell recently asked conference attendees at a recent event if anyone had any spare liquid oxygen. That's the news for tonight. So as always, thanks very much to the Universe Today people for the newsletter. And back to Alice Amanda.
Right. Thank you, Roy. That was really interesting. Yeah. As always, very interesting. Right. Now it's on to our main speaker, Gordon McKay. Now and his talk entitled Controversies in Astronomy. Now, Gordon's got a bit on his PowerPoint with his bio on it, so I didn't bother copying it because it's on his bit. So he's going to tell you all about himself on that. Right, so I'll pass pass over to Gordon.
You get the share screen button. Okay, Gordon, yeah.
Hang on a minute. Yeah, just a minute.
Okay.
I'll just getting this up. Yeah.
Just making sure you had it.
Yeah, I've got it. I've got it.
So,
You seen it now?
Yep.
Let it start. Okay, you got it now?
Yep.
Okay, cool. Okay, controversies in astronomy. This is, it was originally a single presentation, but as I've been working through these, there are so many controversies in astronomy that I'm now working on parts 2 and 3. So the way this came about is that in my study of astronomy at the University of Central Lancashire that I started after I retired, the first paper that I wrote was entitled Controversies in Astronomy. And it was such good fun. And it went down so well that I decided that I would make a little talk out of it. So I hope you enjoy it. The only thing I would suggest to you is that this presentation in itself might be a controversy. So don't shoot me, I'm just the messenger. So here we go. A little about me. I've had a lifelong career in software engineering. I was eventually director of engineering at Thales, the multinational aerospace and defense conglomerate. After that, I went on to specialize in Wi-Fi and mobile network forensic engineering. And I did a lot of work before I retired, the 15 or 20 years before I retired, with government security agencies and law enforcement in the UK and the USA, especially post the 9/11 New York terrorist attacks. So I'm afraid I can't tell you too much about that, because if I told you, I'd have to kill you. So I'm now trying to retire if they let me. And I'm studying astronomy at UCLan, which I'm thoroughly enjoying. I've got my own observatory with a 14-inch SET telescope. And I use a lot of homegrown software tools that I've written myself. And these are performing a variety of astro data processing tasks, plus recently trajectory data processing directly from imaging. My favorite astro work is space rocks. I spend an awful lot of my time obsessing about. And I'm working with several groups on software to process data from a variety of sources, including Pan-STARRS, the Minor Planet Center, and others. And that's all going really well. So that's a bit about me. So first thing I wanted to cover is exactly what is a controversy. Well, the dictionary definition of controversy is a noun, and it's a prolonged public disagreement or heated discussion. And I don't mean the ones that sometimes takes place at home over the ownership of the TV remote. So these are generally about some big important issues. And cosmology and astronomy in general have always been, and some should always say should always be, hotbeds of controversy. And in that way, our science is enriched and progress is encouraged. Now, as I said, they tend to be around big important issues, and examples are numerous, and I'm working on various presentations on this subject. So I thought I would choose some notable ones for this part 1. And at the outset, I should tell you that most of these are stories and tales of some really talented and courageous people, because, you know, our science is full of people who have suffered because of their belief in their truth. So the ones I'm going to cover tonight are heliocentrism, which was basically the shameful Galileo affair. The second one, the Anthropic Principle, which has been used as a universal sticking plaster. The third one is cosmological red shift and the end of the island universe. The fourth one is the real ding-dong battle between Hubble, Vesto Slifer, and Georges Lumetra. And that was a case of belated recognition. The fifth one is all about the giant of a man, Halton Arp, and his intrinsic red shift. The sixth one is about the Big Bang. And here it's to begin or not to begin. That is the real question. The seventh one is the expanding universe. And the last one is time. Is it real? So all of these have been highly controversial issues in the past 300 or 400 years. So let me start with heliocentrism and the tragedy of the Galileo affair. So what was that about? Basically, it was a controversy over the Church of Rome's view that heliocentrism was in fact heretical, and Galileo's punishment for supporting it. So who was involved in this? Well, obviously Galileo Galilei, the Italian astronomer, physicist and engineer, and indirectly Nicolaus Copernicus himself. And the other group that was involved was the Office of the Inquisition of the Church of Rome. So what is heliocentrism? Well, heliocentrism is the belief that the solar system model, the correct solar system model, has the sun at its center. And we all basically accept that as a given. But in days gone by, that just wasn't so. On the left-hand side here, we have the sun-centered solar system drawing from Copernicus's famous paper in 1534, had a really posh Latin name, De Revolutionibus Orbium Coelestium, which is a beautiful sounding name. And on the right-hand side here, we have an antique map from 1568 that showed the Ptolemaic geocentric model of the universe, where you can see the Earth is at the center and the sun appears between the orbit of Venus and Mars. So it's hard to imagine that anyone would at any time believe that the sun wasn't the center of a solar system. But here we have in this painting by the 19th century artist, Joseph Nicolas Robert Fleury. And this is called Galileo Before the Holy Office. And you can see here in the painting that poor old Galileo in the middle here, he's clearly gotten himself into hot water about something, but what? Poor old Galileo was hauled up before the Inquisition in 1633 for openly daring to support heliocentrism, despite repeated warnings from the church to desist. And during the court proceedings, Galileo, though obviously not in English, but he was heard to plead, there must be some mistake here. I was only offering support for Copernicus and his very famous paper some years before, or words to that effect. However, quoting grand sounding titles in Latin fell completely on deaf ears, and Galileo was found guilty of heresy and placed under house arrest until his death, the poor guy. It could be said it might have been worse had Brother Torquemada been in charge. He might have faced a physical torture. Nevertheless, it was a shameful episode in human history. And it didn't happen simply overnight. Galileo's road to the court was lengthy and rocky. And in truth, Galileo had been spoiling for a fight for a very long time. Started off in 1610 when Galileo published his Sidereus Nuncius, Starry Messenger, that means, where he described the observations that he'd been making with his new telescope, including the phases of Venus and the movement of Jupiter and its moons. And then he began to promote, and that was seen as more heinous than support, the theory of heliocentrism expounded by Copernicus. Then in 1616, heliocentrism was officially branded as heretical, and it was banned. Galileo was forbidden from holding, teaching, or supporting such wicked ideas, which is absolutely breathtaking to us in this day and age. Also in 1616, Galileo published his theory of tides and the assertion that this was evidence of the Earth's motion. 3 years later, he published his theory of comets. And all the time, the Catholic Church was getting more and more angry with the guy. He's saying, this has just got to stop. Then in 1632, this was the straw that broke the camel's back. Galileo published his dialogue concerning the two chief world systems. And fatally, he implicitly defended heliocentrism in that paper. That was too much for the church to take. He was tried and he was convicted in 1633. He was held under house arrest until his death in 1642. So I would ask you, we're all amateur astronomers. The next time you happen to enjoy a low power view of the four principal moons of Jupiter, spare a thought for Galileo and all other astronomers who have suffered in the pursuit of truth. And here he is, looking rather glum in this painting. This is in memory of Galileo, 1564 to 1642, and one of his remarkable little sketches underneath. Must be one of the most important sketches of all time in astronomy, despite the fact it's so simple. So the next one, the next controversy, if that wasn't enough, this one begins to get very, very controversial, and it piqued a whole lot of sensitivities in people. And this was all about the Anthropic Principle and the fact it was being used as a universal sticking plaster. So what was this all about? So the controversy was over whether the Anthropic Principle is in fact true or not, or is it just simple human ego and conceit? Was it simply being used to explain anything that was difficult? So who was involved in this? Well, the fact is, for more than a century, there was a whole host of philosophers and astronomers involved in this. So what's the Anthropic Principle mean? So anthropic is an adjective, and it means involving or concerning the existence of human life. Now, they always say, if you're at a dinner party, never discuss religion or politics. And in this case, don't ever discuss the Anthropic Principle, because anything that attempts to explain the how and why of human existence will tend to be a very touchy subject. Man struggles with his possible insignificance and can't easily swallow that, that our existence is some accident. The Anthropic Principle attempts to deal with the apparent reality that there seems to exist a combination of physical laws and properties which preordain the emergence of sapient life, i.e. the human species. In other words, human life is going to appear because the universe is set up that way. It must appear. So from its first appearance, the controversy has raged, eventually become a philosophical sheet of very thin ice covering humanity's deepest sensitivities about our origins. The debate is lengthy and it's complex, with many prominent participants, but let's try and distill it down to its essentials. And I've posed the question here, Is the universe just right for the emergence of life? And if so, why is that? And you might recall that Einstein made a famous remark that although God may have created the heaven and the earth and mankind, did he have any choice in the matter? And that's really a tilt at the Anthropic Principle. So who first started all this business about the Anthropic Principle? Well, it's this guy here, who many of you will recognize as Fred Hoyle. Now, Fred Hoyle first used anthropic reasoning in 1959. And Fred knew well that a single carbon nucleus is formed from 3 helium nuclei in the nuclear reactions which takes place inside stars. But he also knew that that process is very unlikely. So he further reasoned that since carbon is very abundant in nature, something somewhere must have favorably driven that reaction. And he was absolutely right. So here we have our 3 helium nucleuses coming together inside a star, into the stellar nucleosynthesis, to form a carbon-12 nucleus, and some energy is given off. So Fred said that this improbable combination had to be favored by some extremely convenient energy states. Was there some magic afoot here? And such favorable energy states are called resonances. And in fact, they do exist, and Fred was responsible for discovering that. Now, if you carry on with this line of reasoning in stellar nucleosynthesis, as if by the same magic, the discovery of carbon, the destruction of carbon via the addition of a further helium nucleus to form oxygen is prevented by the non-existence of a further convenient energy state, but only by a very small margin. So by the skin of its teeth, all of life-forming chemistry, which relies on carbon, avoids oblivion. So you can see from diagram here that we either are going to go to some sterile, lifeless world, or the blue life-giving planet Earth. Where would we all be without carbon? But this was avoided. And Fred reasoned that this was the same kind of apparent magic. So if you look at the now well-known triple alpha process in stellar nucleosynthesis, you can see that it's also highly ordered. You know, when we have the formation of shells of different atoms, with the ending being the iron atom inside stars in stellar nucleosynthesis. So the question is surely this is no accident. Is it the hand of God or some other grand design? And there are numerous examples of the apparent fine-tuning of very important processes, and but for this fine-tuning would have resulted in situations where life would never have come about. So this is the substance of the Anthropic Principle. And in philosophical terms, it's called a teleological principle. Now that's another big word, and I'm sorry about these big words, but teleological means relating to or involving the explanation of phenomena in terms of the purpose they serve rather than of the cause by which they arise. And I've given an everyday example here, is that we would be to define a pedestrian crossing in terms of a means to cross the street, but with no reference as to how the crossing gets there in the first place. That would be a fairly good example. So the Anthropic Principle began to unfold and caused really vicious arguments amongst various groups of philosophers. The building blocks of life are all created in stars. The Big Bang, if it's to be accepted, only accounted for the creation of the very lightest elements. Stars must evolve, end their lives, scattering their life-supporting grains into space to ultimately form dust, planets, and intelligent life. This must take billions of years, surely. So surely the universe must be very large. It gradually became clear that the old ideas about the Milky Way being all that the universe is, the island universe, can't be true. It simply wouldn't be big enough to provide enough time for complex life to emerge. So here we have stellar evolution and cosmic expansion taking place. It all takes so much time. So the universe must be huge. Otherwise, there could be no life. So the Anthropic Principle still isn't finished with us yet. So yes, we now know the universe is big and it's old. And then along came the discovery of cosmic expansion. So let's imagine that the universe expands at some critical rate. Above this rate, the universe expands forever. And below this rate, the universe ultimately contracts back inwards, becoming very hot and very dense. This is all very controversial stuff and not yet fully decided. Anthropic reasoning additionally holds that expansion slower than the critical rate would have resulted in an implosion before stars and life could form. On the other hand, if expansion had been faster than the critical rate, then matter would have been too far apart for stars to form. Either way, no life. So again, you know, what is this magic that's afoot here? The diagram to the left shows that, in fact, the Anthropic Principle and the controversies it raises is built on other potential controversial thinking. Depending on the material content of the universe, and we, to be honest, we have absolutely no clue right now about the absolute material content of our universe. Its expansion can follow several paths in the future and imply different origin points in the past. So the age of the universe is therefore in some doubt. But we'll come back to that later. For now, the question is, since we humans clearly exist, is there a set of properties, laws, rules that positively preordain our existence? An interpretation of this is highly controversial. And as ever, you know, there's always somebody gets in between the warring parties and tries to broker some sort of peace. And such a guy was the English physicist Brandon Carter, who in 1973 proposed that the two different definitions of the Anthropic Principle should be distinguished. And he declared that there's a weak and a strong Anthropic Principle. He was trying to hold the jackets in the fight, actually. So the weak Anthropic Principle stated that the universe must have conditions required for sapient life, and the strong Anthropic Principle holds that sapient life must exist in the universe. Then, as if to make matters worse, the quantum mechanics groups came along, and they said, well, hang on a minute, for anything to exist, it must be observed. Thus, sapient observers are required to give the universe any meaning. And this turned the whole thing on its head. And this is really tricky stuff. So if you just look at the arguments over the years, in 1904, Alfred Russel Wallace anticipated the Anthropic Principle. And it was argued that even then, anthropic is a misnomer, because life need not necessarily be carbon-based. It need not be human. You know, it could be like the xenomorph in the Alien movies. Who knows what's out there? The principle has also been accused of discouraging a deeper understanding of the universe. In 1950s, Einstein made his famous remark about the creation of the world. In 1961, Robert Dicke argued that the age of the universe as seen by sapient observers cannot be random, but must be in a preordained golden age. In 1973, along came Brandon Carter and proposed that the weak anthropic principle and the strong anthropic principle should be clearly distinguished. In 1986, Barrow and Tipler redefined both of those in their book, The Anthropic Cosmological Principle. And they dangerously brought together two of the most controversial issues ever into proximity, and that was the anthropic principle itself and the cosmological constant that Albert Einstein had proposed about the expansion of the universe. In 1989, Roger Penrose explains the weak anthropic principle in his excellent book, The Emperor's New Mind, but rather dryly reported that when all else fails, people are just using the anthropic principle to explain things. And most recently, Paul Davies in 2006 wrote his book, The Goldilocks Enigma, hypothesizing extensively on many aspects of the debate. And of course, you probably recognize the use of the word Goldilocks in that if a planet sits in the Goldilocks zone around the star, it's the place which is most suitable for life to appear. So it's all about this rather conceited human view that humanity must exist in the universe, and it's all the rules and the laws and the conditions are preordaining the existence of human life. So the next one I want to talk about is cosmological redshift. And this was the heavyweight fight of the century. And before we get to redshift itself, the initial work was proving the extragalactic scale. How big is our universe? And the end of the island universe. But who discovered this and who went on to interpret redshift? Because it's not, I think, who you thought it was or who is popularly credited with this. So who is involved in this? Well, obviously, Edwin Hubble is the guy that's usually credited with the discovery of the speed of receding extragalactic objects and the relationship between distance and the rate at which they recede. And another guy called John Peacock, who was extremely critical of Edwin Hubble and what he claimed to have discovered. So first of all, let's have a look at redshift. What is it? Okay, so as you probably know, redshift is the observed increase in the wavelength of light coming from distant celestial objects towards the red end of the spectrum, presumably because these objects are racing away from us at high speed and stretching the wavelength of those known absorption lines towards the red end of the spectrum. That's really the basis for redshift. So the original hero in this was of course Edwin Hubble, who produced his famous 1929 paper, and it was the basis for what we then called Hubble's law, which relates the velocity at which celestial objects are receding from us and their distance from us. So the further away they are, the faster they appear to be receding. But not so fast. Let's have a close and critical look at his diagram, and that's it on the left as it appeared in his paper. It's purported to be a linear regression of good fit, quote unquote. But in reality, for me as a scientist, it's actually rather poor. And a number of curves provide much better fits. For a start, the number of sample points is inadequate to establish a reliable correlation. And there's an awful lot of, a wide range of observed velocities around the 1 megaparsec and 2 megaparsec distance marks. Now, I'd like to see an awful lot more points And I would like to see a much wider range of distance. Hubble's diagram only covered comparatively very close celestial objects. In good science, we would be looking for much larger data sets and a considerably higher degree of confidence. This in itself makes Hubble's work, I'm afraid to say, mildly controversial. The derivation of the Hubble constant that he came up with was in fact incorrect by a factor of 7. But this was seen as a triumph. Critics, however, didn't see it as a triumph, but simply an invalid conclusion or even bad science. You know, and ouch, that must have hurt. So from here on, there was a good deal of what could loosely be described as a lot of pushing, shoving, and joking for position. And they were, in fact, very exciting times in the early part of the 20th century. So what's all this business about the end of the island universe? So the underlying argument is the actual discussion about how big the universe was, and the fact that Hubble had many opponents. It wasn't originally about redshift and why cosmic expansion might cause it. It was all about the island universe and the fact that the heavens are full of objects at larger distances beyond the Milky Way. So you see from a little graphic here that they used to believe that the Andromeda galaxy was in actual fact inside the Milky Way. And when we looked up into the sky and saw this wonderful band of stars, that was concluded to be the entire universe, and any nebula, any other galaxies that were seen had to be part of this island universe. And some people believed this to their death, you know, despite an awful lot of evidence to the contrary. And just in case you had any doubts about the island universe, if it's on the BBC website, it must be true. This appeared on the BBC website not so long ago. I nearly collapsed when I read it. It took centuries, but we now know the size of the universe. Blimey. Let me know. Let us all know. So, yes, it was all about the end of the island universe. And these objects were found to be outside the Milky Way, these fuzzy blobs, which were other nebula and galaxies, and they were receding at an increasing rate with distance, broadly speaking. But John Peacock here on the right, he wasn't satisfied at all with this. And he wrote a paper in 2013 called Slifer, Galaxies and Cosmological Velocity Fields. And he inferred that Hubble's absolute calibrations were incorrect, and the largest distances were underestimated. Even more disinheriting was Peacock's review of Vesto Slifer's 1917 paper, which Peacock insists that Slifer had reached a much more subtle conclusion in the identification of cosmic velocity. I mean, I suppose that was a really nice way of putting it. After all, you know, this was in amongst all the pushing and shoving, these men are trying to act like gentlemen. But the stage was set for round 2. So what was round 2 in this battle? This is the business of Hubble versus Schleifer, and the controversy about, well, who actually discovered the relationship between redshift, recessional velocity, and cosmological distances? Was it Hubble, as we're all led to believe? So who was involved in this? Well, it was mainly Hubble himself, Vesto Slifer, James Keeler, William Campbell, Georges Lumetra, Dr. Lundmark, Harlow Shapley, Heber Curtis, and others. So many a famous man. But this was here were the principal 2 opponents. Slifer is this dapper looking gentleman on the left, and Hubble, of course, is the pipe smoking chap on the right. And this simmered on and on, this argument. So who should be credited with the discovery that many observed galaxies are much more remote than previously thought, i.e. the end of the island universe? Hubble is regularly incorrectly credited with the discovery of the redshift of galaxies, and much is made of the fact that Hubble could have done more to credit those whose work he might just have benefited from. The measurement of redshift and its significance was understood before 1917 by Slifer. This is him on the left, using his famous spectrograph on the 24-inch Clarkscope at Lovell. And also two guys called James Keeler and William Campbell at Lick. Now, Slifer provided evidence that light from nebula, quote unquote, because some of them were actually galaxies, was strongly redshifted, indicating a high recessional velocity, using his very innovative spectral plate comparison. Slifer's work was described as wonderful in Dr. Knut Lundmark's 1924 paper, and regularly acknowledged by Roger Penrose in his books, such as The Road to Reality and Cycles of Time, both of which I've read. And Roger Penrose goes to great lengths to make sure that Schleifer is not forgotten in this discovery and this argument. So I don't know if anybody's heard about Schleifer, but what else did he discover? Well, he discovered that spiral galaxy rotation was in direct contradiction to Adrian van Maanen, and we'll look at him in the next slide. He discovered that M31 is actual fact coming towards us. He discovered the interstellar medium through his work on the Pleiades, and he also hired Clyde Tombaugh. So he certainly did us all a favour in that particular piece of recruitment. And when he received the Royal Astronomical Society's gold medal in 1933, the president pointed out, in fact, that if cosmogonists, and that's a real word, cosmogonists today, have to deal with a universe that's expanding in fact as well as in fancy at a rate which offers them special difficulties, a great part of the blame must be borne by our medalist, Schleifer. Yeah, so don't forget this guy. Now, Schleifer versus van Maanen is a sort of side story, but it was a tale of grievous error. And there have been many in astronomy. This was a particularly hurtful one for the gentleman involved. Adrian van Maanen discovered Van Maanen's star. It's the closest known solitary white dwarf to our sun. He used a stereo blink comparator to estimate movement of spiral galaxy arms between photographic plates taken decades apart. But the poor chap misinterpreted apparent movement of his reference stars near the edges of his plates. These were in fact smearing and a purely optical effect. The movement was imaginary, and he wildly estimated a rotation period of 10 to the power 5 years, and this had dreadful consequences. It was later recalculated that had his results been accurate, the spiral arms of his galaxy would have to rotate faster than the speed of light. So this was a real come down for this guy. Then there was this guy here, the famous Georges Lumetra, and he entered the argument of Hubble versus Slifer, since he more controversially claimed that the relationship between redshift and recessional velocity had been proposed and demonstrated observationally 2 years earlier than Hubble in 1927. The failure to recognize these important precedents was recognized finally in the renaming of Hubble's law to the Hubble-Lumetra law by the International Astronomical Union in Vienna in 2018. Note, though, that Hubble's name still comes first, despite the fact that Lumetra discovered it earlier. And in this is curious. If you cast your mind back to what happened to Galileo, Georges Lumetra himself was a Roman Catholic priest. He was educated in the Jesuit college. And in 1951, Pope Pius XII declared that Lumetra's Big Bang creation of the world theory provided a scientific validation for Catholicism, which is a rather different kettle of fish from the way that Galileo was treated. However, Lumetra resented the Pope's proclamation, stating that his theory was neutral and it was neither a connection nor a contradiction between his religion and his theory. But, you know, note the curious and obvious difference in treatment between this guy and Galileo. Finally, this guy entered the battle, Michael Way. And in Michael Way wrote in his 2013 book entitled Dismantling Hubble's Legacy, he included this table on the left. And this showed that numerous astronomers were reporting galaxies at distance beyond the Milky Way. The conclusion? Hubble did not discover the extragalactic scale, and he was not responsible for the end of the island universe. And the title of Michael Way's book couldn't be clearer. That you know, it just couldn't be. There was no nice way of putting it. It wasn't Hubble that discovered it. The last round in this battle was involved a guy called Harlow Shapley. And Harlow Shapley, on the left here, it was a vigorous opponent of Hubble's ideas and his extragalactic redshift interpretations. He complained bitterly that Hubble had destroyed his universe through his 1924 announcements. And Shapley took part, along with Heber Curtis, in the Great Debate, which was held at the Smithsonian in April 1920. Curtis argued against Shapley that Andromeda and other similar objects were separate galaxies. Now, we all know this to be simple fact nowadays. Curtis agreed to concede if Shapley's results were shown to be correct. Unfortunately, Shapley had extrapolated Adrian van Maanen's erroneous results for the rotation speed of spiral galaxies. You know, so the whole thing descended into a ridiculous argument. And sadly, Shapley's universe was indeed destroyed, and Curtis won the day. So that was a multi-round battle and controversy that raged for over a century between these various astronomers, with reputations lying in tattered ruins in many cases. The next one I want to talk about is Halton Arp, and I was pleased that Roy in his space news referred to a galaxy which had an ARP number. You don't often see that. But Halton Arp was involved in the intrinsic redshift debacle. So what was this about? This argument was around whether an alternative cosmology might debunk Hubble's law and redshift relationships. So who was involved in this? Well, it was Halton Arp, Geoffrey Burbidge, William Tift, and various others. And I like to think of Halton Arp as he was an extraordinary and passionate man. And I like to think of him as being a guy that refined the art of being wrong with persistence and grace. He was a vocal critic of the Big Bang theory. And let's face it, he may yet be vindicated. He was an advocate of non-standard cosmology, whatever that may be. His non-standard cosmology incorporated an alternative explanation for galactic redshift, you know, shock and horror. And he termed this intrinsic redshift. He's best remembered for his much referenced and fabulous 1966 book, The Atlas of Peculiar Galaxies. Well worth a read and a look at. He published his excellent Atlas of Peculiar Galaxies in 1966, in which he featured 338 galaxies which exhibited peculiar structures. Now, he was originally focusing on the fact that the formation of spiral and elliptical galaxies was poorly understood, and he simply wanted to present examples which would serve as experimental references. Whether it was his plan or not, some of his peculiar galaxies appeared to show associations with companion objects, some of which were quasars. And Arp was not persuaded by the popular explanation that many of the companion peculiarities were caused by mergers. He preferred an ejection mechanism instead. So the theme was set for different interpretations of redshift. How? In his Atlas of Peculiar Galaxies, Arp noted that there were quasars in the foreground of some of his photographs. And in others, there were bridges of material apparently between the galaxy and the quasar. If you look at this picture of ARP194, an interacting galaxy pair, the third object at the bottom appeared to be associated, but is in fact much more remote. It was simply a matter of perspective. But Arp saw that the redshift of these different objects was wildly different. Now, he said because they appear to be connected, there was something wrong with the theory that the further away an object is, the higher its recessional velocity. For him, it had to be wrong. So he refuted Hubble's redshift and instead proposed intrinsic redshift and a completely alternative cosmology. Now, the thing is, Arp's theories were not without support, and they included some fairly heavyweight astronomers and cosmologists, including Geoffrey Burbridge and William Tift. And they even went further to propose there was periodicities in quasar galaxy redshift distributions. I mean, after all, just about everything in astrophysics is subject to some sort of intrinsic periodicity. And the difficulty was that some of Arp's examples appeared to support what he was saying. Halton Arp went to his grave, still arguing his case, still believing that he was right. But most, if not all, of Arp's peculiar galactic morphologies have been explained by improved observation. Of course, we know this now. His intrinsic redshift was and remains controversial and not proven. Similarly, Burbridge and Tift's redshift periodicities or quantized redshift, they're not proven either. If you go onto the internet, you can still see Halton Arp's official website. It's still alive and active in his memory. And some of his objections to the Big Bang and lingering discomfort with cosmic expansion may yet prove to have some foundation in truth. So not everything that Halton was talking about has been disproved and may yet be proven to be true. But he makes his point, even in death, it's like cocking a snoot to the officialdom. His website offers a source of material not ordinarily available to professional journals or the public media. And you can imagine what that roughly translates to. And by the way, Halton Arp was a signatory to the open letter, which openly refuted the Big Bang theory, which was published in the New Scientist in 2004. So he was a renegade to the bitter end. And that takes us nicely on to the Big Bang itself. So what's the controversy about here? Well, there's concerns that there was in fact a Big Bang. And that it might just be it's being forced to fit observations while being adjusted conjecturally and continuously to cope with its many problems. And those involved are just about everyone in quantum physics, particle physics, and cosmological. And cosmological groups. So the Big Bang, it was all going really well. We've all seen images like this one on the right, but which shows the expansion of our universe from a singularity somewhere back in time, like some big funnel that the whole thing is expanding out of. But what lies at the spot marked X beyond the Big Bang? And some people would say, oh, well, you know, that's not fair. You can't say that. You're not allowed to put an X in on this diagram at that point, because that's just not the way it is. But, well, I'm sorry, but there are many people in the cosmological community that want to know and have proven that there's something before the Big Bang. So gradually, the theory was that a Big Bang was followed by a rapid cosmic expansion. And the current lambda cold dark matter type universe appears to provide reasonable agreement with some aspects of the observed universe. A big favorite is the cosmic background radiation, which appears to be provide uniform evidence of the afterglow of the event. The relative abundance of the elements in the universe seems to be explained. And some aspects of the universe appear to be in good agreement with Hubble Lumetra. Okay, there are some glitches and challenges, but things were looking good. Then, New Scientist, May 2004, page 20, there was an open letter to the scientific community. Big Bang Theory busted by 33 top scientists. And the signatures included Eric Lerner, Michael Ibison, and Halton Arp, amongst many others. To quote, the Big Bang Theory relies on a growing number of hypothetical entities, things that we have never observed. Inflation, dark matter, dark energy are the most prominent examples. Without them, there would be a fatal contradiction between the observations made by astronomers and the predictions of the Big Bang Theory. In no other field of physics would this continual recourse to new hypothetical objects be accepted as a way of bridging the gap between theory and observation. It would at the least raise serious questions about the validity of the underlying theory. There you go. That was the headline. The Big Bang Theory and its problems. Most problems with the Big Bang sit in some great big pending tray, waiting for answers and even new physics. In other words, physics that we haven't even thought about so far or devised. And I've put a picture of Fred Hoyle up here because he is in actual fact responsible for the term Big Bang. He happened to describe it as Big Bang quite unintentionally, and it stuck. One of the biggest problems of the Big Bang is that it violates the first law of thermodynamics. Matter and energy can neither be created or destroyed. The formation of stars and galaxies disobeys the law of entropy. It results in a misinterpretation of the redshift. There is not, in fact, the dearly held belief that the cosmic background radiation is homogeneous is in fact incorrect, and has been proven to be so recently. There is inhomogeneity in it. And above light speed, the above light speed of early inflation is counter to relativity. So most of the content of our universe at the moment is conjectural. At least 70% of it is conjectural. So you have to have some sympathy with these guys that are complaining that, hang on a minute, this has just been forced to fit, when in fact it doesn't. Then along comes the the very respected Roger Penrose at Oxford. And he publishes his 2010 book, Cycles of Time, which I've read from cover to cover. And it describes a new cosmology called Cyclic Conformal Cosmology. And he argues it from a prime consideration of the second law of thermodynamics, that the entropy of the universe is increasing. Now, to put this in simple terms, as the universe expands, things become more dilute. The overall density of the universe is decreasing. There's greater distance between things. The entropy of the universe is said to be increasing. But Penrose opposes cosmic inflation following the Big Bang and proposes a relentless march to a maximum entropy state. That is a state where things have become so separated that they will separate no further. And that will be the entry point to the next Big Bang. And he describes each cycle as an eon. I mean, he was popularly opposed Stephen Hawking's change of mind over information loss as it enters a black hole. And it was common at the time that, you know, you were either in the Hawking camp or you're in the Penrose camp, you know, so these were popular lobbies at the time. In Roger Penrose's book, Cycles of Time, he cites concentric structures in the cosmic background radiation. In fact, saying, hang on a minute, it's not homogeneous, it's not even, as we're all saying. He's discovered these structures in it, him and his co-workers, and he cites this as evidence of inter-aeon black hole collisions that have occurred before the Big Bang. So these were structures before the Big Bang. And this is all really heady stuff, but you know, if you want to take a couple of weeks or a couple of months and read it, it's a good read. So the cosmic background radiation is offered up as evidence for the Big Bang and the fact that it's uniform. But is it actually as uniform as proposed? There's an awful lot riding on the fact that the cosmic background radiation is in fact uniform. But Roger and others have claimed to have found inconsistencies. Personally, when I look at that picture of the cosmic background radiation, it doesn't look uniform to me. But then I can't pass an Ishihara colorblindness test, so I'll leave it to the experts. So that brings us to intuitive leaps. The Big Bang has got its problems. The Big Bang has got its supporters. The Big Bang has got its opponents, and some of them are pretty smart guys. But as an astrophysics student, I was told that we must never try to apply intuitive thinking to the Big Bang and cosmic expansion. And that really didn't sit well with me as a student. And we don't want to get hauled up before the Inquisition, do we? But it's possible that we inhabit an infinite space and a moment in existence that stretches back and forward forever. And time and existence are definitely not the same thing. And we're going to go on and look at some of the arguments for that. Cosmic expansion may not be even. And there's a huge reliance on not only the fact that the cosmic background radiation is homogeneous, but that cosmic expansion is even. And skewing has been observed. So it's evident that it's not isotropic as originally assumed or demanded, in fact, by the theory. There is an assumed driving of expansion via negative pressure from dark energy. This may not be true. External effects should be at play and can account for apparent increased rates of expansion. What if there's something beyond the outer reaches of the universe which is tugging things towards it? For An awful lot of people in cosmology, that is heresy to say that. The cycles of time argued by Penrose may yet provide answers. Just before we leave this slide, we should consider that human intuition itself may be as infinite as the universe. So the man in the street is just as capable of intuitive thought about the state of the universe and the whole business of time, the passing of time and existence. It's not simply the domain of the scientist. So cosmic expansion, that comes on from the Big Bang. So what was this about? Cosmic expansion was postulated to be uniform everywhere. This has been called into question now, along with the cause of the expansion and the alleged isotropy and the very nature of the universe itself. You know, heaven forbid. Those involved, just about everyone in quantum physics, particle physics, and the cosmological communities. Cosmic expansion we know is a reality, but there is great disagreement about why, how fast, and the nature of it. Just about everyone agrees that the universe is expanding. A popular theory is that there was a Big Bang, followed by rapid expansion, and that continues. But the rate of expansion increases with distance, and the overall rate may be increasing. But in human terms, the expansion is very, very slow. The rate of expansion at any moment in time is given by Hubble's constant. And you don't need to memorize the number or know the number, but it's 70 kilometers per second per megaparsec. This value has been revised many times. Hubble disagreed with an expanding universe being used as an explanation for the observed data. He himself disagreed. No one really knows what drives the expansion. Various suggestions include cosmic inflation due to vacuum decay, negative gravity, that's a beauty, negative gravity, whatever that means, and some as yet undiscovered particle, you know, like a sort of, maybe a sort of reverse Higgs particle, for example. It's not really a controversy yet, but it's liable to become one. And there's lots of good bedtime reading. So let's just think about cosmic expansion in human terms. It's very, very slow. If we live to 80 years old, that's roughly that number there, 176,601,600,000 seconds. And at a cosmic expansion rate of around 70 kilometers per second per megaparsec, that makes a total expansion of that big number there of kilometers. This is a very large distance, but this is per megaparsec. And a megaparsec is 3.08 times 10 to the power 19 kilometers. That's a monstrous number. So let's say the average distance between us and our TV set is around 3 meters. That means that by the time we reach 80 years old, and assuming that cosmic expansion affected all space, it doesn't, by the way. The theory argues that it doesn't affect our living space or our solar system. And assuming that cosmic expansion affected all space, even the space we lived in, our TV set would be point all those knots, 974 meters further away. Now, you're not going to notice that, as in my little cartoon here. Oi, who moved the telly? I very much doubt if you would know that. But current thinking limits expansion to structures which are not gravitationally bound, which is why it's okay that the Andromeda galaxy is moving towards us and our TV set isn't moving further away. Or is it? We don't know. So here's a popular analogy. If we imagine gravitationally bound structures such as galaxy clusters are like coins stuck in the surface of a balloon. As the balloon is inflated, the coins are rigid and they remain the same diameter, but become further apart. The problem is that as time goes by, bigger and bigger gravitationally bound structures, i.e. the coins on the balloon, are being discovered. Now, Dr. Roger Klaus, who is in my department at UCLan, discovered the huge LQG, large quasar group, and it's greater than 500 megaparsecs wide, possibly greater than 700 megaparsecs. That's absolutely enormous. It's mind-bogglingly enormous. So the coins in the balloon are becoming bigger and bigger. And this is a cornerstone of the cosmological principle, that the universe is homogeneous, that there's no lumps in it. And the largest lump, which is thought to be acceptable to fit the theory, is 250 megaparsecs. So you see that Roger's structure is at least twice, possibly 3 times that size. So the whole thing begins to shake at the seams. And to make matters worse, cosmic expansion may not be uniform. This diagram on the left appeared in physics.org in April 2020, courtesy of the European Space Agency. And it shows findings that cosmic expansion is far from uniform, but it's heavily skewed in one direction. Many papers have now slowly appeared questioning the isotropy of the universe and the uniformity of cosmic expansion. And there's a couple of them there, if you care to go and have a read. And there are many more appearing about the discovery of the expansion of the universe. So many dearly held views are under attack. Lots more people are tending to sit on the fence, and we're waiting for, in fact, new ideas, new discoveries before we can move forward with this argument. At the moment, it's all very controversial. So that brings us to this guy, Mr. Einstein. Now, Albert Einstein, possibly the greatest thinker of all time, produced some very elegant mathematics. But even he admitted that, hang on a sec, you know, I believe this to be true, but it sits on top of some fairly big assumptions. His field equation here at the top left of the diagram looks actually amazingly simple, but it assumes that the universe is homogeneous and isotropic. And we've just seen in the previous couple of slides that, hey, wait a minute, it's not as homogeneous as we thought, and it's not as isotropic as we thought. Even he admitted that his cosmological constant, the delta symbol there, the second item in the equation, which he put in to account for the expansion of space, even he admitted that this was a fudge factor to account for what was observed at the time. And he later admitted it may have been his biggest blunder. So even the great man himself was tilting at potential controversy to come. And that brings us to time. Time is really important aspect of all of this. And the question is time real? So what's this about? Time has been woven into the fabric of cosmological thinking as a component of space-time. We can't imagine there being a situation where time's not real, and surely that can't be true. But in physics and in astrophysics, it's got difficulty finding a home. In quantum gravity and in other aspects of quantum physics, some don't believe it exists at all. So who's involved in this? Well, Minkowski, Einstein, Julian Barber, Smolin, Carroll, Sakharov, and others. And these are all heavyweight names in the fields of astrophysics. Now, this lady here is Sabina Hossenfelder, and she is utterly amazing, this woman. She's a prolific physicist and mathematician. She's got a prodigious media output. If you go onto YouTube and look at some of her videos, she has a remarkable talent for taking the most difficult topics and questions and making them more easily digestible to the world at large. And she produced a video on YouTube left called "Is Time Real?" It's very short, it's 17 real minutes, but it's typically excellent. It covers the growing controversy concerning this thing we call time. But let's start with what we definitely know for sure. For us, time is definitely passing. Now, general relativity was the thing that Albert Einstein, the theory that Albert Einstein created and then revised with his special relativity. And although it may not be the correct theory, it does need time. It doesn't work if there's no such thing as time. Now, if you listen to Sabina Hossenfelder, she'll tell you general relativity is a good approximation, and many people believe that. But it does need time as a dimension. But some things don't need time. If you look at the difference between general relativity and quantum theory, and I've highlighted this particular comparison here in the third line, space and time, general relativity claims that space and time do not exist independently. In other words, they are intimately linked. There can be no space, no time without each other. It's all space-time. In quantum mechanics, it embodies the classical 3 dimensions of space only. Doesn't need time, doesn't want time. They don't like to talk about time. So going back to the Big Bang topic, general relativity doesn't cater for a singularity, the supposed jump-off point for the Big Bang. So we've got a real problem here. Big Bang supporters elegantly sidestep this by saying that the Big Bang deals with cosmic evolution, not creation. That's a bit of a cop-out, if you ask me. General relativity is incompatible with quantum theory, and the drive that we have towards a unified theory of quantum gravity is a rocky road. There's much speculation, but one thing is agreed: it doesn't need time. So who else doesn't need time, and who's arguing that time doesn't exist? Because for us, that must be utterly bizarre as we spend each day spending our time. Well, there's a guy called Julian Barber and others who simply don't believe in time at all. On the left, this is Julian Barber's new book, The Janus Point. Some physicists believe that the past, present, and future all coexist. That's scary. Absolutely. But then it would make it easier to win the lottery. Some believe that time goes forward in one universe and goes backwards in a parallel universe. Some, like Julian, don't believe that time exists at all. And Julian worked, I think, quite bravely for more than 33 years outside the academic institutions. He doesn't like the pressure of having to publish. And his book, The End of Time, was interesting, where he proposed that time doesn't exist. His latest book, The Janus Point, looks to be even more controversial. Now, this is what he believes. He believes that time is only an illusion. For him, existence is a series of what he calls nows. So if we blink our eyes and open them, what you see is now. And a few minutes later, there's another now. And if you add all these nows up, this gives the illusion of time. That's what the guy believes. And for him, the Janus point isn't a singularity like the beginning of the Big Bang. The Janus point is where one big crunch ends and a new big bounce starts. So it's a bit similar to what Penrose is saying about the universe becoming more and more and more dilute till it becomes a maximum dilution. Then it comes back together again for another big crunch. And this progression of nows is what Julian believes gives us the illusion of time. Now, I'm sorry, I personally, I can't quite get my head around that, but that's what the guy believes. Even more bizarrely, this guy here Sakharov, the Russian, he's okay with the Big Bang and the need for time, but he believes that from the singularity, the Big Bang proceeded forwards and backwards in time simultaneously. In other words, the present day exists in both the forward and backward time arrows. And I've put it up there in Russian because I can't get my head around it, and it might as well be in Russian. So it's all going towards its eternity, Jim, and we wish we could know it. This is another school of thought which is gaining ground based on it's all there before our very eyes. There are big bangs or crunches and bounces everywhere into infinite time and space in all directions. And this was actually something similar to the ancient Tao cosmology. The ancient Chinese believed this. Material flows with increasing acceleration gravitationally into the most influential coalescing gravity sinks for the next crunch and bounce. And you get something like this chrysanthemum diagram on the left, where the yellows are the bangs and the reds are the crunches and bounces. And, you know, obviously, if this was true, we would observe skewing in the expansion, which we do, according to ESA in their 2020 data. And it also fits the entropy arguments of people like Penrose. And this could explain increasing expansion rates. And I also like to make one point that obviously Vera Lynn was a believer, because we'd obviously meet again, but we don't know where, we don't know when, in some other crunch and bounce. So let's finish up with the Controversy Hall of Fame. Here they all are: Galileo, Carter, Slifer, Hubble, Peacock, Arp, Shapley, Curtis, Hoyle, Michael Way, Burbridge, Tift, Penrose, Hawking, Barber, and finally Sakharov. But what about this guy? Why is he missing from the Controversy Hall of Fame? Well, that's because you'll have to wait until part 2, because he occupies a great deal of that with his Bohr-Einstein debates and many more. And just one final thing. Maybe these guys knew more than we thought. Is this the real life? Is this just fantasy? Caught in a landslide, no escape from reality. Open your eyes, look up to the skies and see. Thank you. And I hope you can join me for the next crunch and bounce in Controversies in Astronomy, Part 2.
Brilliant. Oh,
That was really good.
brilliant. Like the ending.
Yeah.
Yeah,
I'm
brilliant.
glad you enjoyed it.
Yeah.
it's-
We were
I hope
singing
it wasn't too tech.
at the end.
No, it was really good.
Well, if anybody wants to ask any questions about it, I'm happy to answer.
You want to put it on
Do you
the
want
other?
to stop the screen share, Gordon, and then we can see each other
Okay,
again?
so how do I do that? Screen share
Down the bottom.
down the bottom. Where am I? Where am I?
With no escape from reality.
Close it, just close it down, Gordon.
That's it.
That's it. Mhm.
Managed it.
Oh gosh, what have I done?
And for those that need to, if you go up to the top right, you can click on gallery view again, and that gets us all back together.
Yeah.
How do you think, which sort of interests me, I used to go down to the Astronomy Now conferences in London, and there's a Professor Alan Chapman from Gresham College in Oxford. I don't know, he's quite well known as a sort of space historian, or not space historian, just a general historian. And he was talking about Galileo. I think he came out with a book about him. But essentially, you know, we have, as you just said, there's this thing about the Roman Catholic Church was dead against the scientific outcomes. But essentially what his argument was, that Actually, any science in those days was done under the aegis of the Roman Catholic Church and had been for about 500 years.
Yeah.
The main problem was Galileo was an absolutely obnoxious bastard, and
Yeah.
nobody liked him.
Yeah, he
And
was
essentially
spoiling.
what-
He went for it. He worked hard at getting done.
Apparently, he was so obnoxious, and he annoyed some really powerful people.
Yeah.
And eventually, they thought the only way to shut this guy up
To
is to
lock
stick
him
him
up.
on a show trial and get rid of him. And that's
Yeah.
precisely what they did. And he said, in terms of the science, the Catholic Church did very little about trying to destroy the books or anything. So they sort of accepted what he said, but I thought that was just an interesting way of
Yeah,
looking
that's
at it.
that. Yeah, it must be true, Roy. What you say is true, because Georges Lumetra, what he was saying was far more damaging in that respect, but he got away with it, you know. So Galileo must have been really spoiling for a fight.
To be fair to the Roman Catholic Church, they did pardon Galileo. Unfortunately, it took him to 1992.
No, I'm glad.
I think the Anthropic Principle is quite well. A really good talk, Gordon. I was absorbed right throughout. Very good. And some controversy I never realised about controversies relating to the Big Bang as much as you outlined. But I think for me, the Anthropic Principle, to me, it comes down to sort of what's more likely, that the universe was created for human or even intelligent life, or we just happen to be in a universe that has coincidentally these fine tuning.
Yeah.
For me, the latter is much more probable, especially if the theory of multiple universes is true. Then you've got a clear argument that we just happen then to be in one of the
Yeah.
So to me, the Anthropic Principle, it tends to get too much religious argument in court.
Yes. I just wondered why we needed it. Listen, we're here.
Yeah, exactly. And I read Paul Davis's book, actually. It didn't grab me at all, his arguments, because he's really arguing for the point that the universe is created for humans, and he does talk about this quantum argument of it. Yeah, the universe needs to be viewed by intelligent life. It doesn't. I'm not. Just doesn't grab me, I must admit.
I don't buy it.
No, that's interesting.
I don't buy it.
Yeah.
The strong argument, and which John Gribben advances in one of his books, he takes as far as it's quite all right for us to build nuclear weapons, and it doesn't matter how much brinkmanship we engage in, because we will always live in the universe where the nuclear conflict doesn't happen. But if you apply that reasoning to our individual lives, nobody ever dies in their own cosmos, because you're always in the cosmos where you yourself don't die. And when Carl Sagan did his Gifford lectures at Glasgow Uni, and I put that to him, and he said, what was it? How did he phrase it? A wrong argument has been exposed.
The same as the argument of free will, isn't it? And even if we don't have free will, we should live our lives as though we do. Otherwise, anarchy.
The number of astrophysics textbooks, that I've read that roundly scold you for trying to think intuitively about what may be beyond that. Don't think about that. You're only going to get yourself into trouble. What? I don't accept.
With regard to the Big Bang, obviously there is. You highlighted a lot of controversy I wasn't aware of. What is your overall thought about
on the Big Bang? I tend to align myself. I've read most of Roger Penrose's books. I mean, it takes a long time, and The Road to Reality was as thick as 3 telephone directories, but I read it, and I got my head around the maths, and I read Cycles of Time. I tend to think that there was something. Big Bang wasn't the beginning. It can't be. I think time goes infinitely back the way and forward. And the universe goes infinitely in all directions. I think that any bang was local, and we're expanding, and it's beginning to skew, as the ESA data showed, towards something. You know, there's other things out there, and why not? You know, why not? Why should we're just proposing another island universe? All that we see is all that there is. But we fell down that plug hole before. Let's not fall down it again.
Good, yeah.
That has interesting implications for my unpublished work. When I started writing full time, I was writing science fiction, and I was working in two imaginary universes, one of which was a Big Bang universe, and the other was a steady state universe. And people kept, but the Big Bang universe was an oscillating universe based on one of Opic's books. It was, you know, it collapsed, was reborn, collapsed and was reborn. And for a long time now, astrophysicists have been telling me, no, that's all wrong. I also had ideas about panspermia, which biologists kept telling me were all wrong. But some of those are now back in fashion.
Yeah.
And if the oscillating universe comes back into fashion as well, I might as well blow the dust off that novel I never published.
Yeah.
Try again.
I'm working on a book myself called Towards Extinction, which I'm hoping to, I've written 18 chapters. I'm hoping to finish it soon, before I die. Or I might finish it in the next crunch.
All I know is I've learned an awful lot has happened since I took my astrophysics in the last 10 years. Thank you for that, Gordon.
Yeah, it's absolutely riveting. It is riveting. And I hate the way in which, you know, the ordinary everyday thinking man is told, don't you dare think, you know, that's for us big boys, you know, that's for men, not boys. Anybody can think.
So notwithstanding the fact that the Big Bang might be a local event, do you like Lawrence Krauss's interpretation of how the Big Bang was started?
I'm not familiar with that. What did you say?
Oh, this is Lawrence Krauss. He wrote a universe from nothing.
Oh, I'm not familiar with that. Sorry.
I should read that. It's really very. If anybody else has read it. So he's
got it. I haven't read it yet.
Yeah, so it's definitely a good read. It's basically saying that, you know, it's a definition of what nothing is, and it's basically a quantum principle of particles popping out of existence. That happens all the time, and so I can't explain it exactly. He explains it very well in the book, and it's one of these books. Obviously, like a lot of these popular science books, when you're reading it, it all seems quite rational. That when you try and explain it yourself, you can't do it. But he basically, it's basically a quantum physics. He's a quantum physicist,
right?
Yeah. So he described it as things, something can arise from what is essentially nothing, but it's not nothing. There is actually some quantum movement there.
Yes.
Right.
I watched a YouTube video recently, A Journey Through Time, and there was Professor Brian Cox and others contributing to it, you know, and I was left, you know, I was nearly slashing my wrists, because it was all about the, you know, we're all expanding and the stars are going to finally burn out and the last one will twinkle and the universe will be cold and empty, you know. And I'm thinking, you know, what madness, what heresy, you know. You can't destroy energy. You cannot destroy energy. So where does it all go? You know, it has to go somewhere. No, we live on.
Yeah.
Mm.